All right, so we are going to do a contour integral. And this is going to be very familiar to the last section. It's almost exactly the same even. We just have a different setting. So the words and the symbols we're going to use are different, but the effect is the same. So we're going to integrate the function z bar over the contour c given by 3t plus it squared. Now if we think about this for a second, if x is 3t and y is t squared, then t is like x over 3, so t squared is like x squared over 9, but y is t squared, so that's y is x squared over 9. This is just a parabola. We're just integrating over a portion of the parabola, the portion from -1 to 4. Okay, so I'm going to erase this, but we're just integrating over a parabola. So that's all we're doing. So like in the previous section. All right, so let's go ahead um, and do this. So we integrate over c z bar. Oops, messed that up. Z bar dz. Okay, so what do we need to do here? We need to do two things. We need to plug in our z into z bar, so I'm going to do that. And then we need to plug in our z into dz. So to plug z into dz, well, z is written as 3t plus it squared. If we differentiate 3t plus it squared, we get 3 plus 2ti. And then, of course, dt. So what we're going to do is we're just going to leave the symbol I there and just differentiate like we normally differentiate. And so we're going to get 3 plus 2ti dt. And what are our bounds here? So now that we have t plugged in, we can plug in our t bounds. That's t is -1 to 4. All right, so let's compute that conjugate. So we get 3t minus it squared. And then we multiply with this guy. Cool. And now we multiply this out. So we get 9t plus 6t squared I minus 3t squared I. And then we have a negative I and a plus I here for this guy. That'll be a positive 1. So we're getting a positive 2t cubed dt. All right, let's now that we've check me, make sure I did that right. Let's collect our real and imaginary parts. Let's see, 6t squared minus 3t squared, so that's going to be a 3t squared I. Cool. All right, and we can do one of two things. We can just integrate like normal, and the I comes along for the ride. Or if it makes you feel better, you can separate this as two separate integrals where you integrate the real part, and then you integrate the imaginary part, and you remember to stick on that I. I'm going to write it like this first, just to emphasize that I is really a constant that just comes along for the ride when you do these integrals. So just emphasizing that I is a constant. All right, an antiderivative of 9t is 9 halves t squared. An antiderivative of 2t cubed is t squared over 2, or t to the fourth over 2. Whoops. And then we're going to evaluate that from -1 to 4. And then we got I, an antiderivative of 3t squared is t cubed. We're going to evaluate that guy from -1 to 4. So as you can see, it's the same as just doing finding an antiderivative of the whole thing and then evaluating that from -1 to 4. But I've chosen to write it this way. Let me fix that plus sign. All right. Now I have no desire to plug in these bounds and compute the difference, but I encourage you to. And what you should get is 195 plus 65i. So that's our solution here. And that's it though. So let's do a quick recap on how to do a contour integral right here when we have an explicit parameterization. So what we do is we replace all of the instances with z with our parameterization. That's similar to last section when we replaced all the instances of x's and y's with the corresponding parameterization. So it's the same thing. And then we need to get rid of that dz. And the way we get rid of that dz is we take our parameterization and we differentiate that guy with respect to whatever the variable is, in this case t. And that'll give us a way of getting rid of that dz and replacing it with a dt. And then you just do arithmetic, and whenever you see an I, it's like a constant and it comes along for the ride.